favorite artist electronics here, Mr. Q12 Experiments. I bought because I've seen my friend circuit and also its components, and we talked about them, and I realized my American friend is having better components than the cheap low power components I had before discussing this problem with him. So the stronger I had is this BD681. You can see it's marking there. It's the strongest I had. It's 40 watts transistor, and I use it here on this heatsink. But that heatsink is gigantic for cooling down only this transistor size. And in his experiment, my friend from America, check this out, exactly 49.9, 50 degrees Celsius. I wanted to catch it right now. That is exactly 50 degrees Celsius, because it slowly rised up, and in the course of 3 minutes, 4 minutes like that, from 40, exactly 40.0, it started, and like very quickly it ramped up to 40 from 25 degrees. That is the ambient temperature right now in my room here, and most probably on the table as well. And it ramped up to the 40 very quickly in a couple of seconds. I'm not sure exactly, 10 seconds, 20 seconds, and from that 40 it started to slowly rise up, and now I got it to 50. Here is the probe. Is exactly underneath it, and it is staying on the probe there. And this is a weight, is a piece of metal, just to hold these wires not to move around. And it's from here. Yeah, it rised to 51 now. As you can see, this experiment that I'm doing right now here is with the transistor alone, without any kind of heatsink except the metal that is having around him. And if I'm putting, yeah, it's very hot. Now it's 53. I believe it will stabilize at some point, so around 50 degrees Celsius. So now I'm having 5 volts at 0.22. It means 220 milliamps, or 0.22 amps right now. Why 0.22? Because at 5 times 0.2 is 1 watt. But I give it a little bit more higher here, a little bit of 10, in order of 10 milliamps, to balance, to actually have 1 watt over the transistor, because I measured its voltage, and it was 4.88 voltage drop on the transistor itself between its emitter and collector. So this entire metal casing is the collector, and this pin here is emitter, this one. And how do you know which is which? If you are looking, here is my batch, 10 of them, and if you are looking on them, you believe the pins are on the middle, but they are a little bit over the middle. So if you are dragging a line, an imaginary line here in the middle, you will see these two pins are a little bit higher. So with this is more space here than it is here. That's the idea. That's how you recognize it, the position, probably the writing, but yeah. And this is the pinout. They were quite cheap, like $5, 10 of them, but expensive if you wanted more, like 10 or 100 of them. Anyway, so that's the idea. So right now I took the measurement. I put my multimeter over this pin. So this is the emitter here. This is the emitter, this wire here, and this is the collector, the casing, the metal casing. And I took the measurement between this pin and this casing, and I got 4.88. 120 millivolts is consumed by this other side of the circuit. So what you are seeing here is the power for the entire power for the entire circuit, which is this thing here, and the power that I really need to read is for the transistor is when I'm getting the values, when I'm measuring it. So that's what I'm having here on my paper. So I measured 4.88. Here is the first value that I took, it exactly at 0.2 at 200 milliamps, and I got a little bit less than 1 watt, and that's why I decided to lift it up a little bit more higher, and I obtained this pretty spot on 1 watt. So let's see, here is 54 degrees Celsius. Actually it's 55 now. If I'm letting it here, this 55 is actually after 10 minutes, probably more than 10 minutes. This guy here is very cold, very cold. It's not even warm, which is good. So all the power is over this transistor here. By the way, this is how I got the deal. The selling was 2 of them, and I have them here. You can see them here, and 2 at 0.2. This one. So I have 2 resistors at 0. You see 0.2 ohms or 200 milliohms. These 2 at 50 watts. And to replicate, I took these 2. Well, I only wanted 1, but the deal when I buy them from AliExpress was for 2 pieces plus transport tax. So yeah, I took 2 of them because that was the deal. And also 2, so 1 ohm at 50 watts. You can barely see the markings. So I really wanted the 1 ohm to buy. Yeah, you see 55.5 now. But for this particular experiment, I was kind of obliged to buy this 0.2 200 milliohms to be as close as possible to my friend experiment. The name of the transistor is 2N3773, as you can see here. It's rated at 150 watts, 140 volts with 60 amps, through them. It's an NPN BJT, and that's the, you see, the reading on them, base emitter and collector. And I'm very, very disappointed that it is getting this very low wattage, 1 watt at 50 degrees Celsius. Well, 55. It's kind of stabilized right now at 55. Probably I should insert this here instead of the 50. So I corrected it. It's 55. It's kind of stabilized right now. Yeah. 150 watts that I'm having is way more better as a power transistor than my American friend had on his table. But his was running way more better at higher wattage than what I'm having here. What I'm thinking, maybe he is doing the same mistake as I did. As you can see, I'm using very, very thick wires here. These blue wires. This thinner black wire that you are seeing there is only for the base. You see that there is the base of the transistor. It doesn't need a thick wire there, but only for the collector and emitter. There in the middle is the collector, which is the case of the transistor there. And also these power wires are here, and these power wires here and here. What I got in my earlier experiments when I made the experiments with this BD681, I used very thin, like this base, black base wire that I'm having here. Everything, all the wires were this dimension, very thin dimension, not as thick as this or like that. I was getting voltage loss over the wire itself. So I changed all this wiring, and probably I should change here inside my circuit, especially this wire. Probably it is thick, it is a little bit thick, and these are thick, but probably I should put even thicker wiring, like stupid thick here, to be certain that my entire circuit tracking is not permitting any loss on the wire itself, that the wires are conducting properly without overheating themselves. When you have a voltage across a wire, I actually measured the wire. I put my voltmeter, and I got, well, in different position, in different points, I was getting different voltages. That is how I realized I am having voltage loss on the wire. And also, when I checked the wire, when I put my hand on the wire itself, it was warm. When it was this thick, like this, but when is this thickness that I'm having here, this is completely fine. The wire is not getting warm anymore. But probably what I'm thinking, maybe he is getting some losses in his circuit and he is not aware of them. Like my experiment that I did before, like I explained with my BD681 with these thinner wires. But here with very thick wires, he should probably use more thicker wires not to have losses, because if you remember, when I did the test for 681 with the radiator here, big aluminum radiator there, I got to actually I got to 40 watts for the entire circuit. There, if you remember, I had 8 volt 5 amps. Yeah, probably like that, 40 watts. But remember, this display is for the entire circuit, including the wires and the tracks. So that's the trick that you have to keep an eye on. So that's this is cooking here for probably half an hour. Yeah, and it's stable. It's stable. Yeah, it's 55 for sure. It increases. I move it a little bit when I touch it, and it increased back to, yeah, it's still 55, 56 maybe. But it's good. It's good. It's good. I really wish below 50, but to have it at exactly 1 watt is okay if it's going a little bit up. It's fine. Yeah, this is 56. This potentiometer here is extremely sensitive. I stayed like probably 5 minutes to obtain this 0.22. I was getting 0.220 relatively easily by luck, but 0.22 I was struggling like 3 minutes, or 5 minutes until I really get it onto that 0.22. I was rotating from here and looking there, and while I was rotating on my potentiometer, I was looking on the amperage, what this amperage was telling me. But usually it was jumping to 0.8 to 0.05 or something. It was jumping all around because the potentiometer is sensitive, and the range, the travel of the potentiometer is very short, and you have to like that. And it's because the voltage and also this resistor. And if I'm increasing the voltage, the range, as small as it is right now, it will get even smaller. It will jump like fucking hell. It will jump. I will not be able to make it precise like I'm having it here, to get my precise value of amperage. And also this resistor, if I'm increasing its value, it will enlarge the travel of the potentiometer. I will not touch it because I touched it already, but it will change there very quickly, and I don't want that. Yeah, this is 56 now. Anyway, so that's it. I'm very disappointed about the power and the thermic dissipation by itself alone, and you will see why I'm very disappointed, because of what he was telling me about his transistor, which is weaker than what I have here. And I buy these guys that you are seeing here. 50% I believed him, 50% I didn't believe him. I was like 50-50, you know. I'm still 50-50. Maybe there are in this world transistors extremely good that are supporting a lot of heat dissipation and they are more resilient to power than these motherfuckers that I'm having here, or this. All right, that's it for this part. I actually stayed and searched for all this data that I was discussing with my friend, and this is my friend DL324 from All About Your Kids. Actually, it's what I'm saying here, just to be clear from the beginning. I'm not criticizing, I'm not saying anything bad. He is a very, very knowledgeable guy, and he helped me a lot. So all my respect to him. He is a great guy. He's an older guy, older than me, and I really appreciate his help. The discussion started with LM317, and I am planning to test LM317 as I tested these transistors. But until reaching that, I must have a very good and reliable transistor, not tester, but circuit, and my transistor to actually support a lot of wattage over it, not to crap itself. The temperature got up to about 80 degrees Celsius after about a minute at 10 watts for his transistor. His transistor, by the DL324, this is my friend, my American friend name. So DL324 transistor is a 2N3442, which I'm having it here. And this is it. And it's 10 amps, 140 volts, 117 watts. Yeah, I mentioned it here as well. 140 volts, 10 amps, and 117 watts. So this is the rating his transistor is running at. And my transistor is even more powerful. It's still 140 volts as his, but 60 amps than 10, and 150 watts than 117. But his transistor is running at 10 watts, and the temperature got up, but never reached 80 degrees Celsius after 1 minute. Yeah, probably, but for 10 watts, I don't believe it. So in about a minute to get 80 degrees Celsius, it's realistic, but at 10 watts, I don't think so. I didn't have any problems with dissipation up to 50 watts. What? What? 50 watts? With no heatsink. But it wasn't take me more than 10 or 20 seconds to do the testing. You don't get, at 50 watts, you don't get even 1 second because it will burn up instantaneously. No, I don't believe it. But I will tell you what I don't believe. I don't believe something else, and I will get to it. Next, this is later. I put him to take a temperature at 30 degrees Celsius. So surprisingly, the temperature got over 30 degrees Celsius at less than 5 watts. So let's say around 5 watts. I don't believe this either. If I run it long enough, so for, I don't know, 5 minutes probably, 5 or 10 minutes, he made the experiment. I'm guessing here. So it got over 30. No, I don't believe it. I believe him as a person saying the truth, but I don't believe his data. This value is 50 watts with no heatsink and more than no way. No way is impossible. But there are some arguments that I was thinking why he is getting these values. And these are my arguments. I mentioned it here in this. This is my answer to him. I tested. This is my test that I did. I tested one of my transistors there, this 2N3773, and exactly at 1 watt over the transistor, not from the power supply, for the entire circuit, it got to 55 actually here. It got to 55 degrees Celsius alone and with no heatsink. So this is my data. But remember that I'm having very, very thick wires. And I didn't mention these thick wires here to him. I should probably. I just mentioned this detail with a voltage loss in the power wire. My power supply voltage is 5 volts and 0.22 amps from my power supply voltage. But this is for the entire circuit. And the measured transistor voltage is 4.88 volts on collector emitter. Now here I have a little picture where I took the voltage with my digital multimeter. I put a probe on the collector and another probe on the emitter, and I took the voltage over those two pins. And I got this 4.88, but not 5 volts as my power supply was supplying. And times 0.22 amps, let's say it's, usually there are a lot of amperage losses in a circuit, but let's say it's constant. I should have measured this amperage as well through the transistor, but let's say it's this value that we are having here, and I was getting this exactly 1.07 watts. I believed my friend, my American friend, he is telling the truth. But there, I mean, he is telling the truth, but his data is messed up big time because is not corresponding at all with my my tests that I did. I will say that my tests are closer to the truth than his tests. That's what I'm saying. So because of those thick wires, that's why. So let's continue here. Or I got some medium transistor silicon die inside, like a BD139 silicon die, for example, and encapsulated as a high power transistor. So pretty much like a fake, but with a weaker die, silicon die. Let me show you how a silicon die looks. Like this. This is the die. It's a piece of silicon. Think of it either like a piece of glass or like a piece of rock of some sort. It's having that granulation of a rock. And that's the contacts from emitter and base probably, and this is the collector, here the case, and this is how a die is looking. I'm just randomly looking on the internet to show you what I'm talking about. So that die there, that silicon die, might be from a very weak, for example, this BD139 that I have a ton of them, it's, for example, is what I know, but it might be something else. But the idea is that this is medium power transistor. This BD139 is not low power, it's medium power, and this is high power. What I bought here, this is actually high power. The idea, what I believe, it might be a medium power silicon die inside the high power case, pretty much. It might be this argument, but I believe him, my friend, my American friend, that he is having a stronger high power transistors like this model that he's having, this 2N3442. I believe the Americans have the best of the best. It might be that case as well, and that's why I'm very, very disappointed. So maybe yours are American made and mine are China made. The thing is that I never seen something like your descriptions, and I was very curious to actually see it work like that in my hands. So that's my disappointment about. I was really hoping to see, I don't know, 10 watts, that 10 watts that he is mentioning, this without any kind of heatsink on it. If I was getting that 10 watts without heatsink, I was very happy. But getting it at 1 watts and also 50 degrees Celsius, well, 80 degrees Celsius in his case. But from my experiments that I did, I reached a little bit like over 1.2 watts, 1.3 watts, a little bit over, and it got to 80 degrees Celsius like that, like fuck, you know. So a very small increase in wattage, the temperature increases exponential. So no, it's impossible for in my experiment that I did, it's impossible to reach 10 watts by itself without any heatsink. That's the thing. That's what I really wanted, you know. And I really wanted a 10 watts at 50 degrees Celsius. That's what I wanted to see in my hand, to actually see it and measure it. And fucking hell, yes. But no way. It might be that he is having American made, extremely well made, and the composition of that transistor silicon die, like I said, American made. Maybe that composition is way more wattage stronger than the rest of the commercial transistors that are very power weak by themselves without heatsink. Again, I'm specifying all the time without heatsink, by itself, naked in the air, like I tested it on the table that you've seen there. So in the end, I will add an aluminum radiator over it, like I did with my other tests that I did so far, to make it work at higher wattage. But the idea of this test was to make it and see it work by itself, naked in the air, in the wind, with no aluminum radiator and small size, because heatsink aluminum is occupying a ton of space and eating a lot of space, and without heatsink, it will occupy a very small size, no circuit, and not overheat that much as my other small medium transistors that I tested, like my BD681. I will have a movie and present my test to you. Is this movie that I'm making right now? I know you insisted to put the circuit to 9 volts. His circuit, he made it at 9 volts, and I tested it at 5 volts, but I'm having a problem with the potentiometer. I explained this already. The travel is very small, and if I'm increasing the voltage, it will get even smaller, and it's absolutely, I cannot use it. So I have to change something in the circuit there, and I know already what I can change. Either that power resistor, power load resistor, or probably a resistor, another resistor somewhere else. I was thinking to add one ohm resistor instead of that 0.2 resistor that he used. I'm working as close as possible to his circuit with 0.2 that he used, but I'm thinking to add my 1 ohm resistor just for the potentiometer to calibrate it, to enlarge its travel. I hope this will do the trick. I hope. I have to test it to actually and see exactly if it's actually doing this enlargement of the track, and and that will allow me to find adjustment to do with my pod. And this is the last thing with this that I added right now while I was making the movie. Maybe he didn't, and this is my stronger belief. Although he is mentioning he used an American gauge wire, number 19 gauge number or something, or 16. I forget what number, but I know it's an American diameter. I believe it's diameter of the wire is in gauges or something. I remember he was mentioning he used some thicker wire as well, but I'm not completely assured by his thicker wire, because let me draw you a little bit. Because so this is the circuit here, and here is his thicker power wires, these two. But inside, if he is using thinner wire to the transistor, or thinner tracks to the transistor, to the power load resistor that is having, this is the power load resistor, this is the transistor there. So if he's having smaller or thinner tracks, there all the dissipation, the temperature, power dissipation will be on those tracks, and voltage losses as well. And if it's voltage loss, is also power loss, and also heating up. The problem with his data, not with his explanation of things. He is a great guy. You are a great guy, Mr. DL. I know you will watch my movie, and I thank you for that very much. I believe what you said until here is true, but I don't believe the data and I am also disappointed because I believed your data. That's the thing, that I really, truly believed your data. I was hoping I will get close to these values that you are showing here, and even higher than this. I mean, for this example that you are making, this circuit that you are making, you can get out with power losses inside the circuit. It's fine, it's okay. And read this 50 watts or 10 watts, whatever you have there, only for testing a little bit. Like in your case, you were testing transformers. In my case, I want to test other components, or probably even transformers, as you did as well. But until then, I will test other smaller components. I want to be reliable for hours to keep it on. to keep it in power, everything, to work for hours, for days, or for years even. I want to leave it work like that at 10 watts or 50 watts or whatever, slightly less than 50 degrees Celsius, somewhere around 30, maybe 40 degrees Celsius. That's my target. That's my project. That's my idea that I was concentrated all the time, and I'm still into this idea, how to make it work consistently and reliably at a very high wattage, ideally by itself without any heatsink, because heatsink will occupy a ton of space. So without any heatsink, it will occupy a very small space. So that was my idea, how to make it reliably and consistently and for a very long duration work at a very high wattage. That was my project. I hope you will not misunderstand my presentation and how I'm talking and how I'm explaining things, because my intention is to make something work reliable. So yes, that's my presentation. This is my tests. Okay, that's it for this episode. Thank you very much for watching. I hope you understood something important about transistors along with my experiments. And it's better to experiment by yourself and figure out how stuff works, because one is to watch it and another is to actually experiment it and to put your hands onto it and deal with the problems and figure out why shit doesn't work as you expected and as it is mentioned in the fucking datasheet. Because in the fucking datasheet is mentioned 150 watts, and by itself alone at 1 watt is crapping itself. The bigger the heatsink, the closer to its maximum power rating in his datasheet you will get close to that value. That's my idea. That's what I want to explain. This is his transistor, my friend. His maximum rating transistor is 117 watts. So if he is using a brick like this for heat sinking, of course from aluminum, not from clay, but this size, he will get to this maximum wattage this transistor will run at. And my suspicion is that he can run it even higher than this with this kind of brick. And theoretically, it should run at this wattage at 25 degrees Celsius room temperature, not 50 like I'm specifying in my experiments. Like my American friend said in one of his comments, and he is completely correct, and I'm also agreeing with him, that there are processors that are running 50 degrees or even higher temperature for years, non-stop, like those servers in a server computer. Those processors are running non-stop, and they are getting a restart of the system a couple of seconds, once per, I don't know, 6 months probably, or once per year, but all the time they are running non-stop. They are heating up to 50, 60, probably 80 degrees Celsius. Okay, that's it for this part. Thank you very much for watching. Thank you very much for listening, and see you next time with your favorite artist electronist, Mr. Q12. And if you liked my subject, please leave a like. And don't forget that I only ask for 1 like, and as you can see, I don't have any advertisements running anywhere, so say thank you for that. All right, thank you very much for watching from your favorite artist electronist, Mr. Q12. Bye bye.